So today I will talk about theorem of alternative and Gale matrix and stress matrix. So I will show you how can we use the theorem of alternative to prove some, and the Gale matrix to prove the some theorem about the stress matrix. And the stress matrix is related to the EDM completion problem. So yeah, I'm basically following the book of Abdul Faki. So what's the book? Let me show the book. The book. This is the book. Euclidean. So the book is Euclidean distance matrices and their application in rigidity theory. So, so I will go through. I will just introduce the important theories in chapter 8, and the chapter 8 also is connected to chapter 3 and chapter 1. Chapter 2, so use some theorem from previous chapter. Okay. So on Tuesday, so I talk about this how the infeasibility certificate, right? So basically we have a theorem like that. So for linear equality, we have if you want to certify the feasibility of a linear equality, a linear system, then we have another problem, which is feasible. So there are two statements. So exactly if one of the problem is infeasible, it means another problem is feasible. No, and vice versa. So so we have polynomials over C. So this is called Hilbert's non-standardized, and we also have this linear inequalities, which is the Sarkis lemma, right? Where we have exactly two statements, and we have two statements, and exactly one of the statements is true. So all these theorems are similar. So basically, if one of the problems is feasible, is if only another problem is feasible. So now we can. There is actually a theorem of alternative in the semi-definite programming. So until we have this theorem of alternatives for linear equalities for polynomials. Right? Today we introduce another theorem of alternative in the semi-definite programming, and this is semi-definite programming. This theorem usually is the key to prove a theorem about this this stress matrix. So the main theorem I wanna prove is this theorem. So let GP be an R-dimensional bar framework on n nodes. So R is less or equal to n minus 2. This is 2. So then there exists an n minus 1 dimensional bar framework GQ. So which is equivalent to GP. If and only if there does not exist then there are a positive semi-definite stress matrix omega of GP. So this n minus 1 dimensional framework is the maximum dimension we can lift right? Because there are only n points. So the maximum dimension is n-1, and this so this framework GP is liftable to maximum dimension if and only if there does not exist a non-zero positive semi-definite stress matrix omega. So this theorem is basically it's just a EDM version of the theorem alternative. Okay, so yeah, before I so I want to introduce some basic notation and first. So yeah. So we define this matrix G. J is equal to I minus 1 over n E transpose. This matrix is the matrix that we can so-called the so-called centering matrix, right? So if you have some coordinates or points, and then you multiply this multiplied by j, then all these coordinates are centered. So yeah, so this so j square is equal to j, and the rank of j is n-1. So and the j defines orthogonal projection from SCN. So here SCN is the symmetric matrix and which are centered. So it means if it is in the orthogonal space of E, right? So this J defines orthogonal projection from the centered space to the n-1 symmetric matrix space. And yeah, and we have J times B times J is B if B is already centered. And now we define V. V is the matrix we can factorize J. So we factor J equals to V, J equals V times V transpose. And V is n times n-1 matrix. Okay. So we had four column rank. Yeah, and then by using this way, we can define the mapping or the linear operator FV is equal to FV dot is 1/2 times V transpose times V. This is the mapping from the hollow space. The hollow space just means so SH S sub HN. This space. This means all the matrix is just the set of the n by n symmetric hollow matrix, i.e. the diagonal entries are zeros. And here this mapping is from SHN to Sn-1. So because this its matrix is hollow, right? So diagonal is 0. So it has the same SHN has the same dimension as the n-1 times n-1 the space of the n-1 times n-1 symmetric matrix. So basically our EDM matrix is a hollow matrix because the diagonal of EDM is zeros. And the PSD matrix are in Sn-1. So the inverse mapping from Sn-1 to SHN, we define it as like, so KV is the inverse mapping. So which is K V times V transpose, where K is just this. K is the diagonal x e transpose plus the e times the diagonal x transpose plus minus 2x. So basically, k is kx ij is just xii plus xjj minus 2x xij. Yeah. Okay. So now we have two mappings. So FV is the mapping that is a linear operator that maps the EDM matrix to PSD matrix, and the inverse mapping KV are the maps the PSD matrix to EDM matrix. So KV and the FV define an one-to-one correspondence between the hollow matrix H of order n and the symmetric matrix of n minus 1. And also we defined a one-on-one correspondence between the EDM of a matrix of embedded dimension R of order n, and the PSD matrix of order n minus 1. So by using these maps, we can when we study the EDM, we can actually study it in the PSD cone, right? So that's how we that's the idea. So yeah, we we use this one-to-one mapping between EDM matrix order n and PSD matrix order n minus 1 to study this the stress matrix. Okay. Yeah. So far, are there any questions about this this stuff?
This is okay. Now, the one part that I'm not so sure about is when you define the theorem of alternatives. Did you state it in the beginning? I mean, why is that different from Farkas lemma?
Which theorem?
Yeah, this theorem of alternative.
Yeah,
I mean,
this is this
exactly
theorem.
Farkas lemma.
Yeah, this is exactly sorry. Yeah, I should, yeah. Let me talk about the proof of this theorem alternative.
Okay.
Yeah. So this theorem says let A0, A1, AN be given matrix in Sn. So n by n symmetric matrix, and assume A0 is positive semi-definite. And then exactly 1 or 2 seems true. So there exists x in Rm such that A0 plus x1 A1 plus dot plus xm am is strictly positive definite, right? This is strictly positive definite. Or there exists the y being non-zero matrix and the positive semi-definite, such that the trace of y ai is 0 and the trace of y a0 is 0. Y a0 is 0. So this theorem is basically the hyperplane separation theorem, right? So first it's obvious that both of this so these two statements cannot be both true, because if 1 and 2 are both true, then trace of then you have a trace of y and ax, right? It's strictly positive. It's positive. Like ax be this ax. It's just x1 a1 plus xm am. So if 1 is true, then this ax is strictly positive semi-definite. Therefore, and if y is positive semi-definite, then trace of y ax is positive. But this is impossible because trace of this is just equals trace of y is 0 plus the sum of trace of y xi ai. And then this is 0 and other than 0. So there's a contradiction. So there's a positive on the left hand here is positive, here is 0. So there's contradiction. So it can't be both true. Well, now to prove the other direction. Yeah. So let's assume the first statement is not true. So there does not exist X such that this A0, this affine space is this affine combination is strictly positive. So that means this cone there's a so this cone of a positive. So that this PSD cone intersecting AX, right? It just only has 0. Right. Yeah. No. Yeah. So no. This is wrong. So this AX intersecting this S plus this this matrix of this set of matrix that strictly positive semi-definite, right? This is the matrix of PSD matrix of a positive definite. So this the intersection of these two sets is empty. So you can let's draw a picture. So here this is the set of the strictly positive semi-definite strictly positive definite matrix, and this AX it's lies on this so like this, right? So this is AX. So of course AX is contained in this. AX is affine in this is this affine subspace. Of course AX is contained in this matrix, right? AX is contained in this space, is contained in a linear subspace. So let's say AX bar, which is X0 E0 plus X1 E1 plus XM AM. So yeah. So AX AX is contained in A bar X, and A bar X is a linear subspace. So therefore you can find so given two convex, so you have given a convex set S plus n and the linear subspace, if they only if their intersection is empty, or the intersection of the intersection of A bar X with the interior of the PSD cone is empty, right? Then you can find a hyperplane that separates these two sets. there's a hyperplane that separates these two sets, and and this hyperplane, it contains this this linear subspace A bar X. So therefore, if one is not true, then this A bar X is then there that means that you can find such a Y that this trace of that's such that it defines a hyperplane, and then it contains this this affine subspace, this one. So then I want to show, I have to show that if if there does not exist so if there does not exist X such that this is true, then I claim that A bar X is also there does not exist X such that this A bar X is also positive definite. Why? Because this A0 is positive. It's positive definite. So if you have a x0 xm such that a x0 a1 a0 plus this is PSD, then if x0 is positive, is positive, right? Then you can just scale it to make x0 1. Then you have a contradiction with this. Okay, if x0 is negative, then again I can add because A0 is positive definite. I can simply add just add some x0 bar A bar A0 x0. I can just add this stuff to make it. I can just simply add x0 A0 such that x0 plus x0 bar is 1, and yeah, and the x0 bar A0 is PSD. Is PSD, yeah, and then I have x0 plus x0 bar times A0 times this guy being positive, the definite. So again, that's a contradiction. And if x0 is 0, well, and I have x1, I have x1 I have x1 a1 plus xm am being positive, being positive definite. Well, then I can add a very small, right? I can add a very small, like epsilon A0, and this will because this is very small, and so this thing will be still be positive definite, and then I scale it, so this becomes 1, and then I got a contradiction. So this means yeah, this says if 1 is true, then I can say if 1 does not true, then I can say if statement 1 if there does not exist X such that A0 plus X1 A1 plus XM plus AM being positive definite, then I can say then it's equivalent to saying does not exist X0, X1, XM, such that X0 is 0 plus X1 A1 plus plus XM AM being positive definite. So this is why equivalent.
Okay,
so,
thank you. Yeah.
And then we have a linear subspace, and then we can apply the hyperplane separation theorem.
Okay.
To prove it. Yeah. Okay. Yeah. So this theorem is just hyperplane. It's just hyperplane separation theorem of Bakes lemma. Okay. And yeah, we define this map. And one-to-one correspondence between EDM of embedding dimension R order n and the PS matrix of order n minus 1. And now let's review what the stress matrix, right? So what is stress matrix? So a stress of a bar framework is a real valued function omega on the edge set of graph G, such that this is true, as we have seen many times. So here the summation is the sum of the edges, and omega ij times pi pj is 0. So pi is the coordinates of the points. So and then what is the stress matrix? A stress matrix is the following. So it's a n by n stress matrix, such that omega ij is minus omega ij for ij on the edge set, and it's 0 if ij is not on the edge set, right? So here this E bar G bar is the complement map of G. Yeah, so it's the set of 9 edges, and of course the diagonal of the stress matrix had to be the summation of all the elements that's not the diagonal. So it's easy to say that omega is in the orthogonal subspace of E. All right, so omega times E is 0. So therefore the maximum rank. So the maximum rank is the follow. It's just is n minus 1. The maximum rank of the omega, the stress matrix is n minus 1 minus R. So as R is from the R is from because omega has to satisfy from here, right? So from here omega times P is 0. So P is the coordinates is the point, it's a set of the points which with the such that each row of the P is a coordinates of a point. So this one reduced the rank by R. This P reduced rank by R, and this one, right? This E. So omega has to be orthogonal to E, reduced dimension by another 1. So therefore, the maximum rank of omega is the stress matrix is n minus 1 minus R. Well, here I assume P is center. So P is in E orthogonal. So therefore, I make sure that E is not in the range of P. So E so E can reduce the dimension, the rank by 1. So here we have this theorem, which is very simple. So if P is the configuration matrix of the r-dimensional bar framework, and omega is the unbiased symmetric matrix, then omega is the stress matrix of this framework if and only if omega times E is 0, omega P is times P is 0, and omega ij is 0 for all the ij in the on the for all the ij on the non-edge set. All right. So this is the characterization of the stress matrix. Yeah, of course here I have to assume that P times E is 0. So P is center, so all the points are centered. Yeah, actually I think it's P transpose times yeah, P is it's this, right? So P1 P2 transpose, yeah, P, yeah. Okay. So now let's move to the Gale matrix. Gale matrix. So what is the Gale matrix? So first, let's define the Gale space. So given a Gale n by n EDM matrix B of embedding dimension R, so the Gale space is denoted by Gale D. So GLD. This is defined as Gale D is the non-space of the configuration matrix P transpose. And here is the E transpose. E is the matrix of all, the vector of all ones, right? Yeah. So yeah, E is the 1, 1, 1, 1. And this non-space is of course equal to because I assume that P transpose times E is 0. Then this non-space is just the non-space of P transpose intersecting the non-space of E transpose. So the non-space of E transpose they are this so the non-space of E transpose does not contain the non-space of P transpose. Yeah, because the P transpose times E 0, so the non-space of E transpose contains the range of P. Therefore, it does not contain the non-space of P transpose. So therefore, this one is this definition makes sense. So the dimension of Gale D is the R bar is just n minus 1 minus R, right? So minus R is from the non-space of P transpose, and minus 1 is from the non-space of E transpose. So this is the Gale space. So now what is the Gale matrix? So the Gale matrix is a n times R bar, right? So it's a that forms the basis of the Gale space. Okay, so the Gale matrix is just simply a matrix that forms the basis of the Gale space. So it has a full column rank. Yeah, So this is n times R bar. So the R bar is the dimension of the Gale space. So Gale matrix is the 4-column matrix. It's a matrix of 4-column rank. Yeah, and this Gale matrix has this property such that there's Z transpose times P is 0, and Z transpose times E is 0, right? Because it's from the property of the Gale space. Now we there's a connection between the Gale space, Gale matrix, and the stress matrix. So let's see be the Gale matrix of the bar framework GP of embedding dimension R of n nodes. Then omega, if is a stress matrix of GP of the framework, if and only if omega can be expressed in terms of the Gale matrix. So omega is equal to Z times phi times Z transpose. So Z is the Gale matrix, and phi is a symmetric matrix of n minus R minus 1. And of course, we require that the omega ij, then the entry corresponding to the 9 edges are zero. So that's it. That's the characterization of the stress matrix using the Gale matrix. So the Gale matrix, the stress matrix, the range of stress matrix is just the range of the Gale matrix, right? From this formula. So the range of the.
So what is the advantage of using the Gale matrix? I mean, why not just use the stress matrix? I mean, the definition, in one case, you don't have the transpose. Just have.
Yeah, this is useful to prove things, I think.
Okay.
I think the advantage is to use to prove things, and also you can use this now you have a formula for the stress matrix, right? So given given a bar framework, you can explicitly compute the Gale matrix, right?
You can do in the characterization of the stress matrix that you had earlier, just a little bit scroll up.
Yeah.
Yeah. So I mean, you can do the same here, right?
But here you have a small dimension, right? So phi has a small dimension than the stress matrix omega, right? So omega is n by n matrix, but here this can be the Gale matrix can be explicitly computed, and only phi is unknown. So phi is much smaller. It's n minus R minus 1 instead of. So you want to therefore if you want to find the stress matrix, you can find using the Gale matrix. You are restricting yourself to a much smaller space.
I see.
Yeah. Then there's an example. I'll talk about it. Maybe I can talk this example. Maybe let's show the example now. But I plan to show this example later. But since you asked, let me show you this example.
Well, I mean, instead of using the stress matrix, you could have just used the left null space of the rigidity matrix. That's also the similar dimension as what you have. It's not, I mean, the dimension is similar, right? It'll be n minus R oh, wait, hang on.
the next kernel of the rigidity is r times n, right?
It's n minus r times n.
Yeah, but here
Yeah.
it's phi is n
Yeah,
minus
okay,
r
you're
minus
right.
1
This
times.
is smaller. Yeah.
So actually you can use this advantage to compute the stress matrix.
Well, it's not n minus r. Sorry, it's even. What is it? It's, yeah, it's bigger. It's maybe. Yeah, it's something like n minus r times n. Yeah.
Yeah, because the dimension of the rigidity matrix is what's dimension?
It cannot be more than something like dv minus something. D times
Yeah.
n minus something. Right? So you can think of that as the maximum dimension. So the left null space would be something like dn minus r or something like that. Dn minus r.
And well, this is much
dn or something. So this is a little bit smaller. Okay.
Yeah. This does not involve d, right?
Yeah, it doesn't involve d. Yeah.
Okay. Yeah, and then later I will show you an example how we compute this. How can we compute the stress matrix using the Gale matrix?
Right.
Given a biframework. So yeah, this is the proof is so the proof of the theorem.
Yeah.
So for one, so suppose we so from the definition of the Gale matrix, so we have this Z transpose times P 0, Z transpose E 0, and from the definition of stress matrix, omega P is 0, omega E is 0. So you compare. And now you compare. So you compare these two. So omega is just A transpose times Z, because they have the same. Z is just Z transpose is the non-space of P, and omega is the non-space of P. So there's a linear transformation that such that omega is A transpose Z. Yeah, and they are both of maximum rank. Also, right? And also omega is equal is transmetric, so omega is equal to omega transpose equals Z times A. Therefore, omega is just it's Z times phi times Z transpose, and phi is symmetric. So that's just some simple linear algebra from this two property, right? So from these properties, and of course you want to require that the stress matrix only has non-zero matrix elements for the non-edge set. So we have this condition as well. Okay. So now let's see how actually we prove this theorem. How we connect this to the theorem of alternative. So let's see. Let's suppose GP is equivalent to GQ. So GP is a r-dimensional bar framework on n nodes, and suppose there exists a n-1 dimensional framework by framework GQ that's equivalent to GP. So that means well, so let's say, so D is the EDM of G, right? D is the EDM of GP, and D bar. So here this D bar. So D bar is the EDM of GQ. And then of course then have then GP is equivalent to GQ if and only if FV D bar is equal to FV D plus the summation of YIG FV times of EIG. This is because if GP and GQ are equivalent, then DP is just D minus some plus some YIG EIG, right? So EIG, all the distances in the graph is the same, so it's 0. So only difference is the IJ that's in the non-edge set of the graph G. So this is very easy to see, right?
Yeah.
And then because it's FV, it's FV.
Hey, since we have just 10 minutes left, I'm just wondering if you could just scroll up to the theorem for a second. Just scroll up to the statement you wrote a moment just above.
Yeah.
Yeah. So for the universal rigidity statement, what you want to say is instead of saying then there exists an n-1 dimensional bar framework, what you want to say is you want to write the negation of it, right? You want to say there does not exist an r+1 dimensional bar framework. And if and only if there exists a non-zero positive semi-definite stress of a certain rank.
Yeah.
Minus r-1, I guess.
Yeah.
Right.
Yeah, that's true.
So I mean, you can directly prove that now with this. I mean, you don't have to prove this weaker version here.
Right. Yeah.
True?
Yeah.
Okay. Well, just because we don't have time and we want to, but well, hang on. You're talking next week? I mean, not next week. The week after that. I can. Right. I think in the current schedule we have, sorry to interrupt. I just want to make sure because we're running out of time here. So I think we had Lefty only talking the week after that. I mean, he can start on Thursday. So you actually have some more time if you want.
Yeah, okay. Yeah, I can talk
week after the workshop. Yeah. Go ahead. Sorry, continue.
Yeah. And then because this FV is a one-to-one mapping between the EDM cone and the PSD matrix, and then we have this relation. Just applying FV, and this will be the so this FVD is this is the PSD matrix, right? And FV prime is also a PSD matrix. So we can use this theorem of alternative. So there exists such a this YIJ, and if there exists such a YIJ, then you can say this equal to saying that there does not exist Y is non-zero, such that trace of FVD Y is 0 and trace of FVEIG Y is 0, and trace of 1/2 and this one is just this is just this, and FVEIG is just this. And from the trace of 1/2 V transpose D dV Y is 0, then I can, because this is a dispose of PSD, I could call Y is equal to U, find U transpose, where U is the non-space of KVD, right? U is just non-space of this matrix. So okay, and this and from the second property equation, this is so this is saying that a trace of these guys. I plug in Y, and what I got this this equation, this equality, and my omega will just be let my omega be this, right? It just this one. This is my omega. This will be my stress matrix. So yeah, omega, of course. Then from here, I have trace of omega Eij is 0 for the non-edge set. So this is so one of the properties is met. And now I just need to show that Z times V times U is the Gale space. So how do we actually check that this is the Gale matrix? So I first check Z times transpose E is 0. This means this is because Z transpose U transpose V transpose E is 0, and because J is equals V transpose, and the JE is 0, right? So V G is factorized as V times V transpose. So therefore V times E is 0. So this property is met. Now I need to check Z transpose P is 0. So I need to check this is 0. So how do I so Z transpose P is U transpose V times P. And now I have a range of KVD is range of V transpose dV is range of well, it's range of this. Range of this. That's because V transpose V transpose is equal to V transpose. Yeah, because this is just this is J. So therefore V transpose this. Therefore V this is equal to this. And this again, this will be equal to this, and this will give you the PSD matrix or the Gale matrix, and hence the range of KVD is the range of V transpose P V transpose P times P transpose times V. So the non-space is also the same, right? The range is the same, the non-space is the same. Therefore, U is in the non-space of KVD, which from U is the non-space of KVD. Well, that means U is in the non-space of V transpose P times P transpose V. So therefore, U transpose V transpose times P is 0. So prove this is a Gale matrix. So therefore omega is a stress matrix. So let's finish the proof. And yeah, I guess that's it. I don't have time to talk about applications.